Hello, this is a replay in English of a presentation I gave last week at the Alposs conference in France. Many people know me as interested in running custom Linux versions on tiny devices, but I'm actually interested in running custom Linux versions on PC hardware too. So, I'm Michael Obdenacker. I was the founder of Bootlin, a well-known company in the embedded space. More recently, I started RootCommit, a new company offering training services with a focus on making learning more efficient, easier, more interactive, and more fun. I'm also a long-time free software enthusiast and advocate supporting the April.org association in France, for example. So, why would someone want to test the Mainline Linux kernel? The first reason would be to test the new features that have appeared in the latest releases and to check whether functionality or performance issues that you may have are still there or not. Another good reason is to test future kernels ahead of time before they eventually appear in the updates to the distributions you use several months or years from now. Of course, working with the latest mainline kernel is also necessary to contribute to the Linux kernel by writing code, reporting, or fixing bugs. And last but not least, because using and tweaking your kernel is fun, believe me. Too many people are actually impressed by the Linux kernel, but it's actually a standalone program that's simpler compared to some of the very complex user space stacks you can find. At least I find user space impressive sometimes. Actually, we recompile our kernel all the time on embedded. Here is, for example, a real-life build on Raspberry Pi 5. Here, I'm manually updating the kernel on an SD card that was initially generated by the Yocto tool that many people use in embedded. So basically, here are the steps. First, you get the Linux kernel sources from an archive or from Git. And then in the Linux kernel sources, you set the target architecture, here ARM64. You also have to set a cross-compiler. Here we're using LLVM, which works with most architectures that the kernel supports. We then start with the standard configuration for ARM64, that's here make dev config, which supports all ARM64 boards at the same time. However, this configuration is unnecessarily big for a single board. So to get a smaller kernel and faster build time, we simplify it by running a command like make menu config. Then you save your changes, and you can build the kernel by running make here with 16 jobs in parallel to take advantage of multiple CPU threads on your PC. Then we deploy the kernel modules by running make modules install, but on the root file system of the SD card. We also copy the device tree of the board, that is the description of the devices on the board and on the system on chip, to the boot partition. And finally, we copy the kernel binary to the boot partition too, with the name that the bootloader expects. And then you can see it booting. Let me click on it. There you are. So that's the live serial console of the Raspberry Pi 5 board after changing the kernel. And you could check that at the end, by running uname-r, you can see that it's running the latest mainline at that time. This being said, the situation is actually worse on embedded than on x86. Yes, we know how to compile kernels, either manually or using tools. But most system makers move on to new projects after releasing a product. Or at least they don't provide timely security and bug fix updates to their customers. You could call this ship and run. On x86, the situation is much better as the distributions are updated very quickly after vulnerabilities are found. On the other hand, you can end up running pretty old kernels, as I will show on the next slide. So, a solution for people who want to manage their own kernels is to use a supported stable release from kernel.org. You can see the currently supported versions on the kernel.org homepage and follow the releases link above to know more about the long-term support release plans. So, my goal here is to show you how to build your kernel on the most popular GNU Linux distributions. So I picked Ubuntu 2404, which is based on Linux 6.8, Debian 12.9, which runs Linux 6.1, then Fedora 41 from Red Hat, which runs Linux 6.12. That's super recent actually, at least for now. Then OpenSUSE Leap 15.6, which is on Linux 6.4, And finally, Alma Linux 9.5, which is compatible with Red Hat Enterprise Linux, which still runs Linux 5.14. Wow. By the way, to check which kernel release your distribution runs, you can run the uname-r command, r like release to remember. So here I'm targeting the desktop and server distributions that are actually supported by the Yocto project. Two popular ones are obviously missing, that's Arch Linux and Gen 2, but they are rolling releases and their users have most probably already updated their own kernels. By the way, why am I talking about this topic? The first reason why was that my laptop had a suspend to RAM issue after switching from Ubuntu 20.04 to 24.04. I eventually found that the problem doesn't originate from the Ubuntu kernel, but from its configuration, though I haven't been able to pinpoint the exact problem yet. I originally was recompiling the kernel directly on my PC in a manual way, but that was very slow and inconvenient. Since then, I learned how to do that through packages, which is much simpler to do as it is well integrated with the distribution-specific hooks for managing kernels. Now, the first thing you should do is disable Secure Boot in your BIOS. That's necessary because if Secure Boot is on, only the distribution kernels will be accepted at boot time, not the ones you build. Now, let me explain how secure booting works on a normal distribution. The UEFI firmware, the new name for BIOS, will only boot something signed by Microsoft because PCs are made for Microsoft Windows primarily. Fortunately, instead of the Windows bootloader, we can boot into shim, which is a binary signed by Microsoft, and Microsoft is Linux friendly now. And this binary will accept a Linux bootloader signed by Ubuntu or Debian. This bootloader will then only accept kernels signed by the distribution vendor. Well, it's actually possible to boot a custom kernel while keeping secure boot. You can actually register what are called machine owner keys, and only people with access to UEFI, which should be password protected, can do so. The workflow is a little more complicated, so I found it easier to tell you to disable secure boot instead. But of course, if you want to do more than test the newest kernels and keep your system secure, you should indeed register your own keys. Then, you have to install development packages, typically compilers, Git, Make, and other tools and libraries needed to fetch the kernel sources, to build them and sign them. I'm showing here the exact packages you should install for the three types of distributions. The next step is to get the Linux kernel sources. Here, I'm cloning the stable kernel tree, which contains the stable kernel releases. Then I'm using this git tag command to get the latest tags. This allows me to identify and check out the latest version in a release branch like v6.13.2 when I prepared this presentation. The next step is to pick up a valid configuration for your distribution. Believe me, don't even try to create a working configuration from scratch. While this is still possible on embedded on a PC, that's much more complicated as modern distributions use so many kernel mechanisms. It's very hard to know whether you will need a feature or not. So the only way to get a working configuration is to start from a correct one and progressively modify it. For example, to simplify it, to check whether the changes you make break your distribution or not. Therefore, the easiest way is to copy the configuration for your running kernel from /boot, that's what we do here, and then run make old devconfig to set default values to the new parameters that have appeared in the latest release. For the same need, you could have also run make old config, but this variant asks you to choose a value for every new parameter. That's great when you really want to know what new options are, but if you are in a hurry and the default settings are fine, make old devconfig works better. By the way, this manipulation made me realize that the stable tree also contains the release candidate tags and actually all the commits in the tree from Linus Torvalds. Nice, isn't it? So the stable tree should be fine for most of your testing needs. The next step is to customize the kernel configuration. That's typically to add new features or remove unnecessary drivers, resulting in a smaller kernel that's faster to boot and compiles faster. You will typically do this with make menu config or with make nconfig. Make nconfig, which is shown here, is actually more modern than menu config because it adapts to the colors of your terminal. Like on a dark terminal, it will use a bright text color and vice versa. It also works with transparent terminals. For a very long time, it wasn't really ready for daily use as it didn't have the capability to set values directly from search results, as MiniConfig does. But this has been fixed about 1 year ago. Another thing you'll have to do is remove some distribution certificates from the configuration as you won't have them. To do so, just replace the settings containing .pem with empty strings. You will also need to disable module signing corresponding to the config_module_sig_all parameter. The previous slide was about Ubuntu and Alma Linux. For Debian and Fedora, I didn't have anything to change. Good news! For OpenSUSE Leap, I got an issue compiling one file that I haven't had time to investigate so far. When this happens, and the feature is not critical, just disable it. In most cases, you just have to open the makefile file in the same directory as the file that failed compiling. Look for the .o file corresponding to the .c file, and then you will find which parameter controls the compilation of this file. Sometimes, as it happened here, you have to disable several parameters. That's because of dependencies between kernel parameters. Remember this technique, it works in most cases. Then, building the kernel is very easy, only one command for everything. For distributions with Debian packages, run make bin-deb-pkg, and for distributions with RPM packages, run make bin-rpm-pkg instead. Note that you could also generate source packages, but this matters only when you distribute the packages to others. Here again, I'm speeding up compiling by running 16 jobs in parallel. That's the -j option. Now, let's look at the generated files. In Debian and Ubuntu, the packages are output in the parent directory. The Linux headers package corresponds to kernel headers for compiling more kernel code, mainly out-of-tree modules such as the NVIDIA GPU drivers or the VirtualBox drivers, which are still open source but shipped outside of the kernel tree, by the way. The Linux image package is the most important one, of course, containing the kernel binary and associated modules. The DBG package is mostly the same, but with much bigger files, as they include extra information for debugging. The Linux libc package corresponds to headers for user space applications, typically to allow them to make system calls and exchange data with the kernel. On Fedora and Alma Linux, the packages are built in a subdirectory inside the kernel sources, and there is no debug package, as you can see. On OpenSUSE, that's the same output path, but the versioning scheme is a bit more elaborate. Now, let's install the new kernel. On systems with Debian packages, you will install the .deb files with the dpkg-i command, I like install. Here you see that I'm not installing the dbg package, as it's big and I have no need for it. I'm sure my kernel will never need debugging. On systems with RPM packages, you will install the .rpm files with the rpm-i command. Here, you will note that I didn't manage to install the user space headers as there was a conflict with the already installed ones. That shouldn't be an issue in most cases, as newer kernels are always backward compatible with headers from older versions. You just need recent headers in case you want to compile applications that need recently added system calls. Now, how to boot the newly installed kernel? Well, just reboot the system and the most recent kernel should boot. The only exception was on OpenSUSE Leap, on which I had to run the grub2 mkconfig command to let the bootloader know about the new kernel. One last thing is to keep the ability to boot the default kernel. What you want to have is a bootloader menu allowing to choose non-default kernel versions. To get such a menu on Ubuntu, I had to edit the /etc/default grub file and set grub timeout style from hidden to menu, and then I had to run the update grub command. On Debian and OpenSUSE Leaf, the menu was already there by default, so nothing to do. And on Fedora and Alma Linux, I had to run this grub2 editant command to make the menu visible. To finish, let's reap the benefits of our work, for example by testing the full kernel preemption feature that was merged in 6.12 after 20 years of patient work, by the way. So here we're using the cyclic test benchmark to measure the worst case time between waking up a highest priority task and actually starting to run it on the CPU, whatever the system was currently doing when the task was woken up. That's what is called scheduling latency. As you can see, the worst case is much lower with the fully preemptible kernel compared to with the kernel configured in a normal way. So, here's what I learned preparing this talk. That's what I like about free software, by the way. You keep learning new things. First, I didn't realize that the stable kernel tree also contained everything from the tree from Torvalds. So from now on, I will mostly work with this stable tree. I didn't know about make old dev config either. I was using make old config instead, which is less convenient when all you want is default kernel parameters. I didn't realize how convenient it has become to update the kernel by generating and installing packages. That's much simpler than the manual approach I was using, like in my embedded projects. And I can now compile my kernels on my bigger desktop and deploy them on my laptop in a very easy way. I wasn't aware either that it was possible to keep secure boot with custom kernels, as long as you load your signing keys in the UEFI settings, which can be password protected. Now, here's what you could remember from this presentation. First, you only need the Linux stable tree to get the kernel source code. Second, the main difference between .deb based distributions and .rpm ones is the command you run to build the kernel. That's either make bin deb pkg or make bin rpm pkg. Third, packages make it extremely easy to deploy compiled kernels. Fourth, compiling the kernel should remain for testing purposes. Only the distribution vendor can ensure that all systems get tested updates, in a timely fashion. And at last, packages actually hide the specific ways distribution used to deploy kernels. That's another reason to use binary packages. There we are. Thanks for watching. Here you can see where to get the slides and their sources. Remember, you can use them for your own needs according to the Creative Commons Share Alike license. I also wanted to thank the organizers for the great Alposs conference. First, the town hall of Échirol near Grenoble, then Beldon Communications, the editors of the famous Linphone software, and the OW2 organization, the open source community for professional software. It seems everybody who attended had a great time sharing experience and making connections with other like-minded people. I hope to see you next year. And of course, if you found this content useful and wish to support the creation of more presentations and videos of this kind, you have multiple ways to support Root Commit. Thanks again for watching. Bye, and see you soon.